Hi everyone, we're continuing on with stoichiometry today, but just wanted to remind you that you have assignment 5 at the moment, which for my class is due on the 15th, so other classes is probably a similar-ish date. So make sure you don't forget about that one. You can do that one on Canvas. So we're looking at percentage composition by mass to start with. So far we've talked about the relative molecular mass and the relative atomic mass, etc. So basically we can use that information to find the percentage of an element in a substance by mass. So that's what we're doing. I'm just going to go straight into it for this one. So calculate the percentage of nitrogen in the fertilizer ammonium nitrate. So what percentage of ammonium nitrate by mass is made up of nitrogen? Okay, so percent nitrogen in ammonium nitrate is equal to, so you don't have to write down a formula or anything, but I'm going to just for this first one. So it's going to be the mass or the molecular mass of nitrogen, and there are 2 of them in ammonium nitrate, so 2 lots of nitrogen divided by the formula mass, I suppose it is, of NH4NO3. And because we want it as a percentage, not a decimal, we're going to need to obviously times that by 100. Okay, so let's suss out what the values are. So the same way as last time, we need to find the molecular mass of nitrogen on that page on your formula sheet. So nitrogen is 14.01, I think, or is it just 14? No, it's 14.01, I'm pretty sure. So 2 lots of 14.01, and then we need the full molar mass of ammonium nitrate. So nitrogen is, there's 2 of those, so 2 lots of 14.01 plus, we've got 4 hydrogens. Hydrogen is 1.008, and we've got 3 oxygens, which is 16. And times by 100. Then you just need to chuck that in the calculator. But for the top, you should get 28.02, I suppose. And for the bottom, you should get 80.03 times by 100 gives us 35.0%. So 35% of ammonium nitrate is nitrogen by mass. Okay, another one. Find the percentage composition by mass of each element in glucose. So let's start with carbon. Percent carbon in glucose is going to be the molar mass of the carbons on the top. So there's 6 of them, and they each weigh 12.01 atomic mass units, divided by the whole thing, which is 6 lots of carbon plus 12 lots of hydrogen plus 6 lots of oxygen. And that, if you just, times by 100, sorry. And if you put that in your calculator, it comes out to be 40%. Okay, so for the next element, the percent hydrogen in glucose is 12 hydrogens. So on top, 12 lots of 1.008 divided by the same thing on the bottom as I had in the last example, and that's equal to 180.2. So I'm just going to put in 180.2 rather than writing all that out again. And if I times that by 100, then I get an answer of 6.6%. Now the last one is percent oxygen, which we can do using the same method, but we also know that oxygen is all that's left and that the percentages have to add up to 100%, so it might be easier to just subtract. So I'm just going to say 100 minus the 40% for carbon minus the 6.6% for hydrogen leaves me with 53.4% for oxygen. And that's that question. So that's not too crazy. Okay, next is the mole concept. This is a big concept. So, what is the mole concept? Well, I am going to sort of play a quick YouTube video, which I think might explain it better, because you sort of get the whole visual thing as well. But basically, rather than saying that you're going to buy 24 eggs, you'd say, I'm going to get 2 dozen eggs, right? So we say dozen just to mean 12. Okay, the mole is the exact same thing. It's just a number, and it's a really, really, really massive number, which we need it to be because we're dealing with such tiny, 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 tiny things. So if we're talking about like 12 grams of carbon, we don't want to say how many atoms of carbon are in there because it's just huge, it's just massive. So instead we say how many moles of carbon are in 12 grams of carbon, which turns out to be 1 mole, which is exciting. Anyway, I'm going to show you this video and then I'll talk about it some more. Now I'm going from 2 minutes 39. I'll post a link so you can watch the whole video as well if you want to.
Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So I like that video because it sort of puts it into perspective with the basketballs and the earth and the money. It's a huge, huge number. So where did it kind of come from? Well, you know that they sort of decided that carbon-12 would have an arbitrary mass of 12 and everything else was relative to that, right? So we've said, right, we're saying carbon has this mass of 12, yeah? Because I suppose 6 neutrons and 6 protons. So they got this arbitrary value of 12, which is unitless, I suppose. So for them to sort of make it have units or be more relevant, they thought, well, if we had 12 grams of carbon, how many atoms would we have? And what they found somehow is that in 12 grams of carbon, there are 6.02 times 10 to the power of 23 carbon atoms. So that's where this number has come from. Okay, that's the number of atoms in 12 grams of carbon. They've given carbon this arbitrary value of 12. So that number becomes our very special number, and it's called Avogadro's number, and it is also called the mole. So that's what that number is. 1 mole is 6.02 by 10 to the 23. So if you have 12 grams of carbon, you can say you have 1 mole of carbon atoms. Or you can say you have 6.02 times 10 to the 23 carbon atoms. Okay? All right. You might like to read through the rest of that page. I'm not going to because I think that will be very boring for you to listen to. Here is the number to more significant figures, but we round it to 3 sig figs because we don't want to write that out every time. Okay, so I'm going to move on to molar mass. Now, molar mass is pretty much exactly the same as the other quantities that we learnt about before, which was the relative atomic mass, the relative molecular mass, and formula mass. So it's pretty much the same thing, except instead of it being a relative value, we give it units, and the units are grams per mole. So let's have a look at this one. Determine the molar mass for the following substances. So for communication, we put big M for molar mass, and then inside the brackets P2O5. That means the molar mass of P2O5 is, and then we figure that out. So we need the formula sheet, and on the formula sheet, the molar mass of phosphorus is 30.97. And I've got 2 of those. Okay, I also have 5 oxygens, and each oxygen has a molar mass of 16. So I get my molar mass of 141.9. Now, because I don't have the little r here, that stands for relative, I need to put units on my answer. That's really important. And the units are grams per mole. Okay, so that means, if we had 1 mole of those molecules, 6.02 times 10 to the 23 molecules of this, its mass would be 141.9 grams. So it weighs 141.9 grams per mole. Okay. All right, the next one, the molar mass. Choose a different pen color so they don't get mushed together. The molar mass of CuCO3, what's that, copper carbonate, is the molar mass of copper, and we just have to check these. So copper is 63.54. Plus carbon is 12.01, plus oxygen is 16, and we've got 3 of those. And so my answer is 123.6 grams per mole. And we always give our answer to 4 significant figures because that's what's given on the chart on the periodic table. Okay. All right. How can we calculate how many moles of something we have? Well, we have this beautiful formula. So the amount of moles that we have is the mass of substance that we have divided by the molar mass. Okay, so they have the symbols. The symbols can be a little bit annoying for some people because they're all N's and M's. But little n is the number of moles. Little m is the mass in grams. And big M, as we know, is the molar mass, which we can get from our formula sheets, like we just did. So here we have our first example. Before I go into this example, I'm going to show you this little chart to sort of convert between moles and mass and stuff that I know that Pete particularly likes to use. So these equations are on your formula sheet. This is super handy. We've got Avogadro's number given there, so you don't need to memorize that. It's given the symbol big N with a little a. So that's Avogadro's number. And here we have the formulas. So we're not interested in C equals N over V yet. We're going to cover that later in the year. So we're just looking at the first one and the last one. And it's also got this lovely table here which tells you what symbol is what and what they're each measured in, so what the units are, which is great. So here you've got N equals M over M, and it tells you what they each are if you forget. We also have this top one here, which is big N, so the number of particles that you have, so that might be the number of molecules or the number of atoms or the number of formula units, is the number of moles of the substance times by Avogadro's number. Okay, so the chart thingy-majiggy that Pete likes to use looks like this. And I think it's probably quite a good one. We should all use it. So in the center of everything, we have moles. Moles are very important. Okay, nice little square around that. Now, from moles, we can find the mass of something. So up here, I'm going to put mass in grams. So that's little m. Okay, and a nice square around that one too. And down here, we have the number of particles. Number of particles. And that one has the symbol big N. Okay. Now, we know that the formula to go from moles to mass, we need to do the mass is equal to the number of moles times the molar mass. And that's just rearranging the formula that's on your formula sheet, which is N equals little m over big M. Okay? To go from moles to the number of particles, now I'm just rearranging the other formula. We go number of particles equals the number of moles times by Avogadro's number. That one might not even be rearranged. I think it's like that on the formula sheet. Okay, so that means to go from moles to the mass, I need to times by the molar mass. And to go from the number of moles to the number of particles, I need to times by Avogadro's number, 6.02 by 10 to the 23. So similarly, if you want to go back the other way, you just do the opposite. And later on in the year, we're also going to have our chart going this way and this way when we learn about concentration and volume. So it can be really handy because you're going to get questions where you have to convert from, say, the mass of something to the volume. So you sort of can follow the chart, which is really nice. Okay, now I want to do a couple of examples before I finish the lesson. Sorry if this video is a little bit long. Okay, so in a 50-gram sample of ethane gas, how many moles of ethane are present? So if I want to know how many moles there are from the number of grams, you can either use the chart we just did, or you can look at the equations on the formula sheet and rearrange what you need. So if I look at the chart, I'm going from grams to moles. So I'm going from mass to moles. So I need to divide by the molar mass to find the answer. Okay, so formula for that, I suppose, the number of moles of ethane, C2H6, is equal to the mass divided by the molar mass. So I'm taking the mass and I'm dividing it by the molar mass, obviously. So C2H6, what's the molar mass? Well, I've got 2 lots of carbon, they're 12.01 each, and I've got 6 lots of hydrogen, and they're 1.008 each. And the answer to that is 1.66 mole. Okay. How many molecules of ethane are present? Okay, so I've gone from mass to moles, and now I want to go to the number of molecules. So I'm going to be timesing by Avogadro's number. All right. Excuse me. So the number of molecules of ethane is equal to the number of moles times by Avogadro's number. So 1.66 times 6.02 by 10 to the 23 equals, that's a nice number, 1.00 by 10 to the 24 molecules. Okay, lovely. Next. Which contains the greater amount of substance? Okay, when you are asked to find the amount, what that means is find the number of moles. If you're asked to find the amount of eggs that you have, you're going to count your eggs. So it's the same thing. How many of them are there? Yes? So if you're asked to count the amount of eggs, you might say, I've got 2 dozen eggs. So we're going to do the same thing, find out how many moles we've got of each and which one's greater. So, what is what is the number of moles of sodium sulfate? So it's going to be the mass divided by the molar mass. So I might actually, now don't be cross, but I'm going to calculate the molar mass first. You've probably written that in pen already and now you're shouting at me. So the molar mass of sodium sulfate is, so the molar mass of sodium, which you can find on your formula sheet of course, is 22.99, and we've got 2 of those. Then we have a sulfur, again check your formula sheet, 32.06, and then you've got your oxygen, 16 lots of 4. And that comes out to equal 142.0 grams per mole. All right, so how many moles of sodium sulfate do I have? I've got the mass divided by the molar mass as the formula. So the mass is 25 grams divided by the molar mass, 142.0. And I get an answer of 0.176 moles. And I'm going to give my answer to 3 significant figures because I only have the mass to 3 significant figures, so it would be unreliable to give it any more significant figures than that. All right, we need to compare that with the other one. So let's find the molar mass of the other one, AgCl, silver chloride. It is silver, which is 107.9 off of your formula sheet, and chlorine is 35.45, and that equals 143.4 grams per mole. So now let's find the number of moles in the same way. Number of moles of silver chloride is the mass divided by the molar mass. So it's 30.5 divided by 143.4. And the answer to that is 0.213 mole. So which is the greater number? Silver chloride. So let's answer the question. It's always very important. Silver chloride contains the greater amount. Hooray! Okie dokie, I'm going to finish the page, so I'm going to do one more. And then we'll do the other ones a more different time. What is the mass of 1 mole of water? Now, if you've really understood the concept of a mole, then this question should be fairly easy. If you haven't, which is probably most of you, because it does take quite a while to grasp the concept, then we might do this one using the formulas. So I want to know the mass, and I know the number of moles. So N equals 1, okay? And I know I can find big M, which is the molar mass, because that's just on my formula sheet. So let's go ahead and find the molar mass of water. Oh, what's happening? Why is it doing that? What's happening? Not my favourite. So the molar mass of water, which is H2O, obviously, is 2 lots of hydrogen plus an oxygen, which is 16. And that is 18.02 grams per mole to 4 significant figures. I've just sort of memorised the molar mass of water accidentally over the years. You guys probably will too. So now, the number of moles, sorry, that's not what the question's asking me to find. The question wants me to find the mass of water. And you can use the chart thingy. I hate it when that happens. So we're going from the mass to the number of moles, so I would divide by the molar mass. Or you can look at your formula sheet and look at the equation and rearrange it. So the formula on your formula sheet is N equals M over M. I need to rearrange that for mass, so I'm going to times through by molar mass. I get mass equals number of moles times by the molar mass. So number of moles times by the molar mass, and it's 1 mole, 0.00 if you like, times by the molar mass, 18.02. Surprise, surprise, the answer is 18.02. Now, don't be cross, but I'm going to give that to 3 significant figures because they've only given me the number of moles of water to 3 significant figures. So 18.0 grams. Wonderful. Okay, what is the mass of 1 molecule of water? I can't really use the formulas for this one. I need to try and use my brain, which is okay. Now, I know that this is the mass of 1 mole. Oh, stupid thing. I just want the blue colour. This is the mass of 1 mole of water molecules. Okay, I'm gonna write down my thinking. You'll hate me if this is really straightforward to you, but if it's not, then you might not hate me. So 18 grams is the mass of 1 mole of water molecules. Okay, and what is 1 mole? Well, it's our favourite number, Avogadro's number. 6.02 times 10 to the 23. So it's the mass of 6.02 times 10 to the 23 water molecules. So how do I find the mass of just one of those? Well, I divide by how many there are. So the mass of 1 water molecule is 18 grams. That's the mass of 6.02 times 10 to the 23 of them, divided by how many of them there are. Now I'm going to get a tiny, 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 tiny number. It is, it's not really where I wanted that, is it? Oh, that's great too. It is 2.99 times 10 to the negative 23 grams. You expect to get a times 10 to the negative because it's going to be a tiny, 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 tiny number that's very, 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 very small. I once met a guy who told me that you'd be able to see 1 molecule of water, which is rubbish, complete rubbish. Look how small that is. Anyway, he was wrong. So, next, what is the mass of 1.9 times 10 to the 24 molecules of water? This should be hopefully fairly straightforward. And I know how much one of them weighs, so I can know how much 5 of them or 10 of them or 1.9 times 10 to the 24 of them weigh, just by timesing by how many of them there are, right? So, mass of 1.90 times 10 to the 24 molecules. Sorry, I feel like I've lost the plot a little bit today. I'm not really on my best game. Is the mass of one of them, 2.99 times 10 to the negative 23, times by how many of them there are, which is 1.90, times by 10 to the 24. And that equals a lovely number, 56.9 grams. My face is probably covering up some of these answers, which is not ideal for you, and I do apologise. But if you listen, I read the answers out loud. Now I'm going to find which questions I would like you to practice and write them down somewhere. Okay, so here is this little text box with the questions that I have picked. I think those are the best ones for you to try. There are some others that I skipped there, but it'll just take you forever if you do all of them. You might like to leave some for, I don't know, test practice or whatever. So that's there. Sorry that this was a bit of a long lesson. I hope you enjoy doing the problems, and I will see you next time.